record now to the cloud, and we'll get going. Okay. So, so I already sort of gave some motivation for learning asymptotic methods. And really, I think the best place to start is with equations that you're probably well familiar and experienced with, which is algebraic equations. Okay. These can certainly come up in research applications if you're looking at, eigenvalue problems or something like that. And you may often have small parameters that pop up along the way. So this course, I usually kind of structure things by really just immediately kind of jumping into examples, and that sort of guides the general process of how to perform each of the asymptotic methods that we'll talk about. Again, that calendar will give you sort of an overview of all the different methods that we'll work with. So to start today, I want to talk about regular perturbation methods, and we'll talk about two different methods. One is what's called an iterative method, and the other is an expansion method. And both of these have their advantages. Okay, so immediately with this example, what should catch your eye is this small parameter epsilon, and you're going to come to befriend epsilon. Epsilon is your friend. You want to see an epsilon. If you want to see a small parameter, that means that you can make progress usually in analytical methods of applied mathematics. So of course, you might look at this equation and say, well, I know how to solve this. I've known it for 20 or more years, right? Well, maybe that's just me, so because I'm a bit older, but 15, 10 years, something like that. You just use the quadratic formula, right? So why are we starting with this, right? Well, it's because we have a basis for sort of comparing the perturbation approach that we'll use in order to start with it, okay? So the solution to this equation, if I want to find x, I could just apply the quadratic formula, right? But I want to show you something now that should give us some insight into what's going to happen next. The next thing we could do, okay, is expand using what's called a binomial series, okay? And what's the binomial series? I'll just write it down here. The binomial series is going to be if I have 1 plus y to some power, then I can write this out. This is, just sort of one particular form of an expansion to approximate this for y small. Okay, you can write it out as 1 plus alpha y, alpha times alpha minus 1 to factorial y squared plus alpha times alpha minus 1, alpha minus 2 divided by 3 factorial y cubed, and so on, right? So if we expand, right, the this square root term using a binomial series, okay, what we have when we account for all appropriate combinations, so then we end up with x is either equal to plus 1 minus epsilon over 2 plus epsilon squared over 8 minus epsilon to the 4th over 128 and so on. Or we have minus 1 minus epsilon over 2 plus epsilon squared over 8 minus epsilon to the 4th over 128. Okay, plus, and then so on, okay? And this will converge if epsilon is less than 2, okay? where it has absolute value less than 2. But we said it was positive, so we just epsilon less than 2, right? But we said it was small, so it should always converge for the range that we would be considering, right? It's just you want to make sure epsilon's big enough that it isn't growing faster than the denominator of these terms that appear in this power series, okay? So, right, so who cares, right? Because we're just basically taking an answer that we already know and making it worse by doing an expansion, right? But the idea is maybe if we couldn't go ahead and use the quadratic formula, we may be able to arrive at such an approximation an alternative way, okay? And so the question is, yeah, if we can make such an approximation, is it good, question mark, okay? Well, if I just take epsilon equals 0.1, okay, then what do I get for each term, okay? Well, x is approximately 1 if I just take one term, okay? X is approximately 0.95 if I take two terms, okay? X is approximately, now this is where it gets interesting, 0.95125 if I take three terms. And let's just go out to four terms. X is approximately 0.951249, okay? That's if I just take four terms, okay? And what we'll find in this class is usually you're not going to take that much more than 2 or 3 terms, right? In fact, you may only take like, the first couple of terms. And in this case, if I just take 4 terms and I compare it to the exact formula, okay, x is equal to 0.9512492, right? So just by taking 4 terms of this asymptotic expansion, I get the first 1, 2, 3, 4, 5, 6 digits correct, okay? And remarkably, for some asymptotic expansions, you can even do better than that, right? And now, one point that I want to make, right, that I'm going to come back to again and again, is that usually we want to approximate the equations first, okay, and then solve, right? Which we did not do in this case, right? What did we do in this case? We solved the equation and then we did the approximation, which is sort of throwing away our work from before, okay? So the next part of the lecture, we're going to go through 2 methods of approximating the equation, solving the approximate equations, and then comparing this to this expansion that we got by having the solution first and then expanding it, okay? So let me take a breath and ask if there's any questions so far. All right. So what's next, essentially, is that we need to build some methods for approximating these equations, okay? And one way is what's called the iterative method, right? And so how does the iterative method work? Well, usually what we have to do is rearrange our equation, okay, the thing that I'll call star, so that on one side of the equation we have our unknown variable by itself, okay, x by itself. So x is equal to plus or minus 1 minus epsilon x, right? So I have not solved this equation fully, right? I still have an implicit version of this equation, okay? And this is going to form the basis of some iterative process, right? Now, I could have rearranged this equation another way, right? And then I might try it that way, okay? But this is just the way that I rearranged in this case, okay? And as we handle more problems, we'll talk more about what's the best way to sort of rearrange the equation, okay? But the idea is that given some guess, right, at the solution xn, okay? Let's say that, you know, this is my my nth guess at the solution to my implicit equation, okay? The iterative procedure essentially tells me how to update my guess, okay? And so again, this seems very back of the envelope. Why would this work? Okay. The idea is that if xn is the true solution, there should really be no update to xn in this case. And the hope is that whatever this update is, it will get me closer to the true solution. Okay. So maybe for those of you that have seen this, you know, sort of discrete dynamical systems and things like that, this is a discrete dynamical system, and it's going to have some fixed point, which would be the true solution of the implicit equation, okay? So you can think of it sort of like a cousin of gradient descent or the secant method, okay? Those are all in the same sort of ballpark, okay? And the idea is that we're hoping xn may be better than, xn plus 1 is better than xn, okay? So essentially, when the approximation is good, okay, then we should expect that xn plus 1 is going to be approximately equal to xn, okay? So again, for those of you that have, you know, seen like cobwebbing methods and things like that, the idea is that you would be sort of in the vicinity of the fixed point and you just move a bit closer, okay? So note here, if epsilon is just equal to 0, right? X equals 1 is a root immediately. So that may be what you want to start with, right? So essentially try x0 equals 1 as our first guess, okay? And then in that case, x1 is going to be equal to the square root of 1 minus epsilon x0, which is equal to the square root of 1 minus epsilon, okay? So you might say, okay, well, we're done there, but usually in asymptotic methods, we want to get some expansion where each sort of subsequent term has a similar form. Now, hearkening back to our original expansion, right? We had something like a power series, right? So we may not want to leave this as this. Remember that epsilon is small. So we should be able to do some, you know, Taylor series approximation and then, you know, get some refined version of x1, okay? So if I go ahead and expand, x1 is equal to 1 minus epsilon over 2 minus epsilon squared over 8 minus epsilon cubed over 16, okay? Essentially, again, I'm going to do this by the binomial series, okay? Then I have a power series expansion, okay? And usually what you do is that each step in the iterative process, you're going to keep another term, right? So we don't necessarily want to keep all of these terms, right? But because we started with 1, let's just add on epsilon minus 2 now, okay? So essentially keep one more term than last time, okay? And so we end up with x1 is equal to 1 minus epsilon over 2, okay? That's going to be our next guess, okay? And so then x2 is equal to the square root of 1 minus epsilon, 1 minus epsilon over 2, okay? And what you'll soon find is that sort of each little individual step of a lot of asymptotic methods maybe is, you know, something that you've seen before, right? It's either a, you know, a series expansion or you know, just some messy algebra, right? But sort of put together, you get these really sort of powerful methods, okay? So again, I'm going to expand this, expand. Look at that P working for some reason. Okay, there we go. 1 minus epsilon over 2, 1 minus epsilon over 2, minus epsilon cubed over 8, 1 minus epsilon over 2 squared, minus epsilon cubed over 16, 1 minus epsilon over 2 cubed plus dot, dot, dot. Okay, so again, I'm just using the binomial series. Okay, this is some messy algebra. We have to expand this all out and then collapse it. I will show you the result of that, which is 1 minus epsilon over 2 plus epsilon squared over 8 plus epsilon cubed over 16. Okay, there's no way getting around, sort of tedious, messy algebra and asymptotic methods. That just sort of comes with the territory. Okay, but now we could essentially say, well, our next term that we'll add in is the epsilon cubed term. Now, if I look back right here, that is exactly the first three terms that I get from, just expanding my quadratic formula. Okay, so it seems to be working okay. All right, and then we, could keep three terms, right, and iterate. Okay, but as you'll find, right, this method is a bit laborious, right? And maybe there's a cleaner, sort of more systematic method that will work some of the time, but maybe not necessarily all of the time. What you'll find is that if you don't know what to do, the iterative method is usually the best, okay? Because you make very little assumptions, right? You just say, well, all I'm going to do is make an initial guess. I'm going to, create this iterative map, essentially. I'm going to expand, and I'm going to successively do that in order to build up my expansion. Okay. Another method that you can try, though, is what's called the expansion method. Okay. What is the expansion method? Well, let's talk through it. Okay. First part of the expansion method, we're going to set epsilon to 0, and we're going to find the unperturbed roots. Okay. What are the unperturbed roots of our equation? Right. Well, it's just going to be x squared minus 1. So that means x is equal to plus or minus 1 are our unperturbed roots. Unperturbed just means epsilon is 0. You don't include the perturbation, which is your small parameter. Okay. Second part of the expansion method is to expand your solution. Okay. X is equal to 1 plus epsilon x1 plus epsilon squared x2 plus epsilon 3 to the cubed x3 plus and so on. Now, how did I know how to use that expansion? Well, that's always a good first guess, is a power series in epsilon, akin to what you would get from a Taylor series expansion. Just assume that, if epsilon's small, epsilon squared is going to be smaller, epsilon cubed is going to be even smaller, okay? And each successive term is going to be smaller and smaller, and that's going to be some improvement on my perturbation expansion, okay? Doesn't always work though, okay? And we'll talk about how to solve that problem later. Well, now you take this expansion and you plug it into your full equation, and that's going to look like this, okay? This is going to be a bit lengthy, right? So here's your quadratic term. Here's your linear term. And sorry, I'm running out of space here. And then here's your minus 1 equals 0 term. Okay, so here's your whole expanded equation. And now you have, a bit of tedious algebra to do. right? So you have to expand this equation now and match terms of similar power, okay? The result of that expansion is that you get 1 plus 2x1 epsilon from the first term, right? Because when you square this, you get 2 of these terms popping out. At order epsilon squared, you get x1 squared plus 2x2 epsilon squared. At order x3, just from this first quadratic term here, you get 2x1 x2 plus 2x3 epsilon cubed plus and so on. Sorry, I'm going to run out of space again. I will continue down here. Now for your linear term here, right? We're going to get an epsilon plus an x1 epsilon squared plus an x2 epsilon cubed, so on and so on. And then the last term you have is minus 1 equals 0. Okay? Now, what do you do in the expansion method? Well, you just equate, okay, terms in powers of epsilon, right? So at epsilon to the 0, what do I have? I have a 1 here, and I have a minus 1 here. So I get 1 minus 1 equals 0. Is that true? Yes. Okay. So essentially the expansion already had the right x0, so there's nothing to do there. Okay. What we want to know is what's, x1, right? You see x1 popping up here. So we're going to hope that at next order, we get an equation specifying x1. Do we? Let's see. Okay. At power x1, right, or epsilon to the 1, we get 2x1 times epsilon, but I'm just going to drop the epsilon because everything has an epsilon in front of it. And then I have an epsilon here. So plus 1 times epsilon. And that's all my epsilon terms equals 0. Well, I can solve this, and I get x1 is equal to minus 1/2. Sorry, my lines are sort of running into each other. Okay. So does that make sense? Well, it jives with the expansion we had before. Before we had a minus epsilon over 2 term. So we're getting that again from the expansion method. Let's go to order epsilon squared. What happens there? Well, in that case, we get x1 squared, right, plus 2x2, okay, plus, where's my other epsilon squared term here? X1 equals 0, okay? Now, I know what x1 is, right? That's minus 1/2, so I can plug that in. So if I plug that in and move stuff around, I get 2x2 is equal to minus 1/4 plus 1/2. Or in other words, x2 is equal to 1/8. Does that agree with what I got before? Yes, it does. My expansion before had an epsilon squared over 8 term in it. So the expansion method is giving me an answer that's consistent with my iterative method, which is also consistent with my expansion of my quadratic formula solution. Okay. Let's do one more. Okay. At epsilon cubed, okay, we're doing what's called climbing the hierarchy. And I want you to notice that at every step of the way, okay, the next equation that we get relied on knowing the solution at the previous step in the hierarchy. Knowing x3 requires having known x2. Knowing x2 requires having known x1. And that's the beauty of these expansion methods, is usually you can bootstrap your way up the hierarchy in this way. Okay, so 2x1 x2 plus 2x3 plus x2 equals 0. That's what shows up at order epsilon cubed. So just to double check that, right? Here's, these epsilon cube terms here, and there's my other epsilon cube term there. We just put them all together into an equation, okay? Well, now if I combine all these terms, right, I get 2 times minus a half, so I just get a -1, so I get a minus 1/8, okay, plus 2x3 plus 1/8 equals 0. So this just implies that x3 equals 0, okay? And isn't it true? I don't have an epsilon cube term in my other expansions that I built for this solution, okay? So that's consistent, okay? All right. So, so I think that's enough for expansion method, okay? Let me make a couple remarks and then I'll maybe pause for questions. So first remark is this is easier, right, than the iterative procedure, right? Once you build the expansion, okay, you just have to do a series of algebraic calculations. And in fact, this is sort of easily automatable. You could think that, maybe you could even probably write a code to do this, right? And there are, okay? But note that it requires knowing the expansion in epsilon. And you might say, well, yeah, just do that every time, right? Power series in epsilon. How can that go wrong? It's just not always going to work, especially for transcendental equations, right? Algebraic equations, everything is sort of hunky-dory, right? Because you're living in sort of a powers of x, powers of epsilon world. Once you introduce sines, cosines, logs, exponentials, okay, you could have some much funkier looking expansions, which you're going to need an iterative procedure to sort of reveal to you, unless you've sort of come across them before. And the last thing I'll note is that we sort of climb the hierarchy, okay? So first we find, right, x0, then x1, then x2, and so on at successive powers of epsilon. Okay.
Zach?
Yeah.
So you're saying the power series solution technique doesn't always work. Will we have like examples of that in the homework, or is there a quintessential example you can give us?
Yeah. We'll get to that when we start dealing with transcendental problems. One classic example is logarithmic series, where the series is not 1 epsilon squared. The series is like 1 log of 1 over epsilon, log of 1 over epsilon, log of 1 over epsilon. And there's a number of those that can show up. And once you've had a bit of time to cut your teeth on the iterative method, which we'll do in class, it hopefully will become clear how to sort of build those series up. Yeah. So yeah, logarithmic series are sort of a common alternative to a power series. Okay. Thanks, Sage. Okay. We got about 10 minutes left. I'll just forge ahead and really talk about an extension now of regular perturbation that sort of gets at my power series point here, right? How did I know that I needed to start at 1 in my power series? Why wouldn't I have to start at epsilon to the -1, right? How do I know that my power series doesn't need to be expanded like as 1 epsilon to the 1/2, epsilon to the 3/2, epsilon squared, right? You could imagine a multitude of, even sort of possible regular perturbation expansions that you might have to do, or sort of mild changes from that. Okay. So that really shows up when we start talking about singular perturbation theory. Okay. And I still haven't really told you what I mean by this, but you probably have heard the word singular before. And you know that it sort of means like a non-generic case, right? Maybe something is 0 that really changes the nature of a particular problem, okay? And the idea is that we must use a different approach if the perturbed equation differs fundamentally, okay, from the epsilon goes to 0 limit, okay? And then again, the nice thing about algebraic equations is that we can just explore this in a very transparent way to start with before we start getting into things like differential equations, okay? Now, what do you see about this equation? This is a quadratic equation as long as epsilon is greater than 0. As soon as epsilon 0, it's not a quadratic equation. It's a linear equation. What does that mean? That means that the epsilon 0 equation has one root, and the epsilon is greater than 0 equation has two roots, okay? So how do we deal with that in the case of our perturbation expansion, right? At epsilon equals 0, x equals 1 is our only root. And the question is, do both roots that emerge, do they both emerge sort of from x equals 1? Or does one sort of appear from infinity or something like that? And so let's just dissect that a bit to start with before we go back into perturbation methods in the time that we have left, okay? For epsilon is greater than 0, a new root is, as I was saying, sort of born. But the question is, where from, right? Okay. So if we looked at the exact solutions, okay, we can get an answer to this. X equals -1 plus or minus the square root of 1 plus 4 epsilon divided by 2 epsilon here, right? So you see that when epsilon is very small, right, the minus root here, okay, is going to involve something that's like order 1 up top, but then order epsilon on the bottom. So actually, this other root is sort of appearing from negative infinity. And I can show that here, right? If I plot these roots as a function of epsilon, right, then the plus root is just emerging from 1, right? So this is x plus, okay? But the minus root is sort of arising from minus infinity. So here's x minus, right? So as I send epsilon to 0, this root is diverging, and then somehow in the singular system, it disappears. It's not there anymore, because x equals 1 is the only root at epsilon equals 0, okay? So this is our new root, right? And this is what's called our singular root, okay? So intuition may guide you immediately towards what may have to show up in the perturbation expansion, okay? Probably don't start the perturbation expansion at order 1. You probably need to start the perturbation expansion where? It's a little bit of a leap. What's a function of epsilon that goes to minus infinity as epsilon goes to 0?
1 over epsilon.
Yeah. So your perturbation expansion for that root is probably going to have to involve 1 over epsilon, okay? Or something that diverges to minus infinity, okay? So for small epsilon, we can again do a binomial series, right, of our square root function. We've got two roots, right? We've got the x plus root, which is just going to be well behaved, right? And it's going to look like this. And that works as long as epsilon is smaller than a fourth, okay? And then x minus now, if we just do a binomial series expansion, we get this expansion here, right? So now you see we're involving this sort of singular term that's going to diverge as epsilon goes to 0, okay? So the second root, okay, x minus has an expansion, and I'll just write out the general form, right, which is x equals x, and I'll call this term -1, x sub -1 plus x0 plus epsilon x1, and so on. So the idea is that really we just need an expansion that has an appropriate rescaling, okay, of a regular perturbation expansion. And the rescaling is just take a regular perturbation expansion, divide it by epsilon, and you got a new expansion, you know, just change up the labels a bit, okay? So to carry out the expansion method for this problem, right, we would just sub this expansion into the equation, okay? And we would get what? We would get epsilon x -1 over epsilon plus x0 plus epsilon x1 plus and so on, right? X -1 over epsilon plus x0 plus epsilon x1 plus so on -1 equals 0, okay? And if we go ahead and expand this, right, then we get a 1 over epsilon term, x -1 squared, right? Because to leading order, right, you square this and then you multiply it through by epsilon, right? Plus 2 x -1 x0 plus epsilon 2x -1 x1 plus x0 squared plus, and now let me do the terms from the linear part, 1 over epsilon x -1 plus x0 plus epsilon x1, and so on, -1 equals 0, okay? So that's our long expansion there. That we just got that from plugging stuff in. Okay, I'm almost ending this now, okay? And if we equate the powers of our equation now, we have to start at epsilon to the -1. And we get that x -1 squared plus x -1 equals 0. So that means that I could either have x -1 equals -1 or x -1 equals 0, okay? And this is our non-singular root. And this is going to be our singular root, right? Remember, in this expansion up here, this one does not have a 1 over epsilon term in it. That's our non-singular root. This one does. That's our singular root. If we want to explore the singular root, we would start with this and start climbing up the hierarchy, okay? So then I'll circle back to this at the beginning of next class, right? But the idea is that if we consider the singular roots now, okay? In other words, x -1 equals -1. Then at x to the 0, we end up with 2x -1, x0 plus x0 -1 equals 0. This implies that x0 equals -1, okay? At x to the 1, or sorry, at epsilon to the 1, 2x -1 x1 plus x0 squared plus x1 equals 0. This implies that x1 equals 1, okay? And we can essentially continue to our desired order in epsilon. Okay. So I think that's probably enough for today. Sorry, I went over a little bit, but let me just sum up and then I'll see if there's any questions before we close. So what did we talk about today? We talked about, first of all, regular perturbation methods for algebraic equations. What do those involve? Well, the easiest is to just assume you have a regular perturbation series expansion, plug it in, equate like powers, and then solve up the hierarchy, sort of bootstrapping your way from epsilon to 0 up to epsilon 1. Another way, if you don't know or not sure about the expansion, you can use the iterative method, where you just have to write down a map that gives you some xn plus 1 from some xn that's plugged in. And then if you have a singular method, you should expect that, a singular equation, you should expect that your equation is going to change in some way. And there's a number of ways of sort of revealing that to you. You can guess. There's also a systematic way we'll talk about next time of finding that appropriate rescaling so that you can build an appropriate expansion. You can also sort of try iterative methods too, but sometimes you run into trouble with that if you don't start with the right guess. You won't arrive at the root that you might be interested in. Okay, so that's where we're at now. We'll continue next time by talking about rescalings and also the case of sort of fractional power expansions. Are there any questions before we conclude?
I had a question about the first example with the expansion method.
Yeah.
That one also only gave us the positive root. So how would you get the negative root from that like non-singular case?
Yeah, so you're talking about just this expansion method?
Yeah.
Yeah, so just instead of choosing x is positive 1, you would just start with a negative 1 here. So you just start with a negative 1, and then you can climb up the hierarchy. So the idea is that by choosing x0, you can sort of pick which direction you want to go.
Got it.
Yeah, good question. Thanks, Jake. Okay. All right, anything else?